Here's something that should be scientifically impossible. Right now, starlight from a galaxy directly behind the sun is reaching your eyes. Not light that curved around the edge of the sun by accident. Light that was aimed straight through where the sun sits and got bent around it, like water flowing around a rock, and arrived at Earth anyway. In 1919, a team of scientists photographed this happening during a solar eclipse, and when they measured it, the universe stopped making sense in the way everyone thought it made sense. Here's the part that should stop you cold. Light has no mass. Zero. Not a tiny amount. Not a number so small we round it to zero. Actually, literally, mathematically zero. And gravity, as Isaac Newton described it, is a force that pulls on mass. No mass, no pull. That was the rule for over 200 years. So light should sail past the sun in a perfectly straight line, untouched, indifferent, immune. Except it doesn't. It bends. It bends by exactly the amount a very different, very strange idea says it should. An idea that has nothing to do with force at all. What if I told you that gravity, the thing holding you in your chair right now, the thing that will make you fall asleep faster than you expect tonight, is not actually a force pulling on things? What if I told you that the sun isn't reaching out and grabbing that starlight, and yet the light still bends, because the space the light is traveling through is not the shape you think it is? By the end of this, you are going to look at your own shadow differently. You're going to look at the sun differently. And if you stay with me through everything I'm about to lay out, sit back, because the last hour of this video is going to sit with you long after you've closed your eyes. Before we go further, if this is the kind of question that makes your brain lean forward, hit subscribe now, because we go deep into these ideas every week, further than almost anywhere else on this platform. And I'd love to know. Type into the comments where in the world you're watching this from, and what time it is right there for you. I read these. I've had people writing in from a fishing boat off the coast of Norway at 2 a.m., from a dorm room in Manila at sunrise, from a truck stop in Nebraska at midnight. Wherever you are, whatever time it is for you, you're about to learn something that connects you to every one of them. Because the light bending around that sun is bending the same way over Norway, Manila, and Nebraska, all at once. Let's begin. Let's start with what everybody, including brilliant scientists for over 2 centuries, believed to be true. In 1687, Isaac Newton published a work that would define how humanity understood the universe for the next 228 years. Newton said gravity is a force, an invisible hand reaching out from every object with mass, pulling every other object with mass toward it. The bigger the mass, the stronger the pull. The Earth pulls on you. You pull on the Earth. Yes, technically you do, just an immeasurably tiny amount. The sun pulls on the Earth, keeping us in orbit. It's an elegant idea. It's also the idea most of us still carry around in our heads without realizing it, because it matches everyday experience so well. Drop a ball, it falls. Throw a ball, it arcs downward. Newton's law of universal gravitation predicted the motion of planets with jaw-dropping accuracy. It sent people to the moon later, using nothing but Newton's math. But here's the twist, and it's the twist that this entire video hangs on. Newton's force of gravity depends entirely on one property: mass. His equation, F equals g times 1 times m2 divided by r squared, has mass sitting right there in the numerator, doing the work. Take away the mass, and the force collapses to nothing. 0 times anything is 0. Light has no mass. Photons, the particles of light, are, according to everything we know, exactly massless. Not very light, not practically zero, actually zero, as a fundamental property, confirmed to a precision that would put a Swiss watchmaker to shame. Current experimental limits place any possible photon mass below about 1 times 10 to the negative 18 electron volts, which for comparison is smaller than an electron's mass by a factor with 18 zeros trailing it. So think about what that means under Newton's rules. If gravity is a force that only acts on mass, and light has none, then light should be completely unaffected by gravity. A beam of light should pass by the sun exactly the way it passes through empty space, a billion light years from anything, dead straight, uninterrupted, indifferent to whatever giant ball of plasma happens to be sitting nearby. Under Newton's model, gravity and light simply should not be able to talk to each other. They exist, in a sense, on separate channels. Mass talks to mass. Light isn't part of that conversation. Think of it like a magnet and a piece of plastic. You can wave a magnet all around a plastic spoon and nothing happens, because the spoon isn't the kind of material that responds to magnetism. Under classical Newtonian thinking, light was the plastic spoon and gravity was the magnet. Two systems that simply don't interact, no matter how close you bring them together. Except, and here's your first mind-blown moment, and we're barely 5 minutes in, some of the sharpest minds of the 18th century had already started to suspect something was off, using nothing but Newton's own equations, pushed to a strange extreme. In 1783, an English clergyman and natural philosopher named John Michell did something remarkable. He took Newton's equations and asked a question nobody had thought to ask seriously. What if a star were so massive, so dense, that the escape velocity needed to leave its surface exceeded the speed of light? Newton had calculated escape velocity, the speed you need to break free of an object's gravity, for cannonballs, for the moon, for planets. Michell simply scaled it up, and he found that, mathematically, you could build a star massive enough at even light, whatever light actually was. And remember, in 1783, physicists mostly thought light was made of tiny particles, following Newton's own corpuscular theory. Even light would not have enough speed to escape. He called these hypothetical objects dark stars. Light would try to leave, and gravity would pull it back down, the same way gravity pulls a ball back down after you throw it, just harder. A few years later, the French mathematician Pierre-Simon Laplace independently reached the same conclusion in 1796. Here's what will blow your mind about that. This was a full 132 years before Einstein, and using pure Newtonian mechanics, treating light as tiny massive particles, two separate. Scientists had already stumbled onto the mathematical shadow of what we now call a black hole. They were technically wrong about the mechanism, but they were sensing something true through the fog, that gravity and light were not as separate as the clean version of Newton's theory implied. And that's your foundation. That's the crack in the wall. For over 200 years, physics said light and gravity don't interact, because light has no mass, and gravity is a force that acts on mass. But hidden inside that same math was already a whisper that something didn't add up. That whisper would stay quiet for over a century, until one physicist, working alone in a patent office, decided to stop asking, what force is pulling on the light, and start asking a completely different question. What if there's no force at all? That question is going to take us apart and put us back together over the next 3 hours. But before we get to Einstein, before we get to the eclipse, before we get to black holes and the edge of what we understand about reality itself, I want you to notice what just happened in your own head. A few minutes ago, you probably had a vague, comfortable sense that gravity pulls things down. Now you're sitting with a contradiction. Light has zero mass, and yet it bends around massive objects, and Newton's own force-based model can't explain why. That discomfort, hold on to it. That's the exact discomfort that sat in the back of a young patent clerk's mind in Switzerland for the better part of a decade. And it's about to unravel everything you think you know about falling. Stay with me. In the next section, we're going to step into an elevator that Einstein imagined. A thought experiment so simple a child could follow it, and so deep that it rewired the entire concept of what gravity even is. Here's a question. When you sit in your chair right now, are you being pulled down by gravity, or pushed up by the floor? Most people answer without thinking. Pulled down, obviously, that's gravity. But hold that thought, because Albert Einstein asked himself almost exactly that question in 1907, sitting in a patent office in Bern, Switzerland, and he later called the answer he found the happiest thought of my life. What if I told you that the entire concept of gravity as a pull might be, in a very real sense, an illusion created by your own point of view? Let's build this slowly, because this is the foundation everything else rests on. Picture a person standing in a closed elevator, no windows, completely sealed off from the outside world. That elevator is sitting on the surface of the earth. A person inside feels their feet pressed against the floor. They feel weight. If they drop a ball, it falls to the floor at 9.8 meters per second squared. Totally ordinary. Now, take that same elevator, rip it off the earth, and haul it out into the deep vacuum of space, nowhere near any planet, any star, any source of gravity at all. Attach a rocket to the bottom and fire it so that the elevator accelerates upward at exactly 9.8 meters per second squared, the same acceleration as gravity on Earth's surface. Here is Einstein's revelation. The person standing inside that accelerating elevator in deep space would feel their feet pressed against the floor. Exactly the same sensation. If they dropped a ball, it would appear to fall to the floor and hit it at exactly 9.8 meters per second squared, because the floor is rushing up to meet the ball as the elevator accelerates. From the inside, with no windows, there is no experiment, none, not a single one, that the person could perform to tell the difference between standing on a planet and accelerating through empty space. Einstein called this the equivalence principle. Gravity and acceleration are not just similar. They are locally, physically indistinguishable. Think of it like this. Imagine you're a passenger in a car with blacked out windows. The car speeds up smoothly, and you feel your body pressed back into the seat. You cannot tell from that sensation alone whether the car is accelerating forward on a flat road, or whether the car is parked on an enormous hill, and gravity is pulling you back into the seat as you sit tilted. The push you feel is identical either way. That's the equivalence principle, translated into something you've actually felt in your own body. Now here's where it gets strange, and this is mind-blown moment number 2. If gravity and acceleration are truly indistinguishable, then whatever happens to light under acceleration should also happen to light under gravity, because physics has to be consistent or the whole framework falls apart. So let's test that. Picture that same elevator, out in deep space, accelerating upward. Someone shines a laser beam horizontally, straight across the elevator, entering through a tiny hole on one wall. In the time it takes that beam of light to cross the elevator and hit the opposite wall, the elevator itself has been accelerating upward, so the floor has risen slightly. The beam of light, which traveled in a perfectly straight line from an outside observer's point of view, appears, from inside the accelerating elevator, to have curved slightly downward because the elevator's floor rose up to meet it while it crossed. Now apply the equivalence principle. If acceleration bends the apparent path of light inside that elevator, and acceleration is indistinguishable from gravity, then gravity must also bend the path of light. Not because gravity is pulling on the light's mass. Light has no mass to pull on, remember. But because gravity and acceleration are the same phenomenon wearing different clothes, and one of those clothes bends light as an unavoidable side effect of geometry, not force. Sit with that for a second, because I want you to notice what just happened. We didn't add any new force. We didn't give light a secret hidden mass. We simply asked, what would a windowless observer see? Followed the logic, and light bending fell out of the math almost by accident. That's the moment Einstein realized Newton's whole picture of gravity as a pulling force might be incomplete in a way nobody had noticed for 200 years. Here's what will really blow your mind, though. When Einstein first calculated exactly how much light should bend around the sun, using only the equivalence principle in 1911, he got an answer. But it was the wrong answer, off by exactly a factor of 2 from what nature actually does. It took him 4 more years of work, moving from this elevator thought experiment to a full mathematical theory of curved space and time to get the correct number. I'll come back to why that factor of 2 matters, because it's going to become one of the most important plot twists in this entire story. It's actually how scientists later proved Einstein was right and Newton was wrong, using a single photograph taken during a total solar eclipse. But we need one more building block before that. If gravity isn't a force pulling on mass, what is it? This is where Einstein made his final, most audacious leap. And it's the leap that takes us from gravity bends light a little to gravity reshapes the very fabric that light, and you and everything else, moves through. Think of it like this. And this is the analogy almost everyone has heard. But stick with me, because we're going to go past the cliché version most people stop at. Picture a stretched rubber sheet, flat and taut. Roll a heavy bowling ball into the middle of it. The sheet dips down, curving around the ball, creating a kind of well. Now roll a small marble across the sheet, off to the side. The marble doesn't travel in a straight line anymore. It curves, spiraling in toward the bowling ball. Not because the bowling ball reached out and grabbed it with an invisible hand, but because the marble is simply following the shape of the sheet it's rolling across. The marble isn't being pulled. It's going straight, in the straightest possible line available to it, on a surface that is no longer flat. That's Einstein's real answer to Newton. Mass and energy, and light carries energy, even without mass, don't create a pulling force. They warp the shape of space itself, and everything traveling through that space, including light, simply follows the shape it's given. Light isn't being seduced off course by gravity. Light is going perfectly straight, in the only kind of straight line that exists in a universe where space itself is curved near massive objects. Now, quick retention check before we move into the next layer, because this next part is going to require this exact idea locked firmly in your head. What we've established so far. Gravity isn't a force in the Newtonian sense. It's the effect of mass curving space. And light, despite having 0 mass, still has to travel through that curved space, which means its path bends even though nothing is pulling on it. If that clicked, keep going, because in the next section, we're going to introduce something even stranger than curved space. The fact that space and time are not separate things at all, and that this single fused entity, spacetime, is the actual surface the marble is rolling across. And once you see that, the sun-bending starlight is going to feel almost quaint compared to what's coming. Before we move on, if your mind is already stretching a little, that's exactly where it should be, right now. Drop a comment with the word curved. If this elevator thought experiment just rearranged something in your head, and stick around, because section 3 is where we stop talking about space and start talking about something that will change how you think about your own timeline, right down to the seconds ticking by as you watch this. What if I told you that space and time are not 2 separate things happening near each other, but one single object, and that this object can bend, stretch, and warp the same way a sheet of fabric can be pulled and folded? This is the idea that takes Einstein's elevator thought experiment and turns it into an actual, testable mathematical theory of the universe. General Relativity, published in November 1915. Let's build this carefully, because spacetime is one of those words people throw around without really absorbing what it means. In everyday life, we treat space and time as completely different categories. Space is where things are up, down, left, right, near, far. Time is when things happen, before, after, now. Newton treated them exactly this way, as a fixed, unchanging stage space on which events, time played out, totally independent of each other, ticking at the same universal rate everywhere, for everyone. That matched every human intuition ever formed, because nothing in ordinary daily experience ever suggested otherwise. Einstein's radical claim was that space and time are woven together into a single four-dimensional fabric, 3 dimensions of space, plus 1 dimension of time, fused into one mathematical object called spacetime. And here's the part that connects directly back to our bending starlight. Mass and energy don't just curve the 3 spatial dimensions, the way the rubber sheet analogy suggests. They curve time as well. Clocks closer to a massive object tick slower than clocks farther away. This isn't science fiction. It's been measured directly. In 1971, physicists Joseph Haffel and Richard Keating flew atomic clocks around the world on commercial airliners and compared them to a stationary clock left on the ground. The flying clocks, moving faster and at different altitudes, came back showing a measurable predicted difference of tens of nanoseconds, matching Einstein's equations to within experimental error. Here's your next mind-blown moment. GPS satellites right now, orbiting roughly 20,000 kilometers above your head, experience time passing at a very slightly different rate than clocks on Earth's surface, for 2 separate relativistic reasons. One from their speed, one from being farther from Earth's mass, and therefore in less curved spacetime. If engineers hadn't corrected for this using Einstein's equations, GPS location errors would accumulate at a rate of about 10 kilometers per day. Every ride-share app, every phone map, every piece of turn-by-turn navigation on the planet works correctly right now because engineers built Einstein's warped spacetime directly into the software. You have, whether you realized it or not, personally relied on general relativity being true, probably within the last 24 hours. So now let's put light back into this picture, because this is where it gets genuinely strange. Light always travels the shortest possible path between 2 points. That's a rule that holds in flat space and curved space alike. In flat, empty space, far from any mass, the shortest path between 2 points is a straight line, exactly like you'd expect. But near a massive object like the sun, space-time itself is curved. And the shortest path between 2 points on a curved surface is not a straight line. It's called a geodesic. Think of it like this. Picture a commercial airline flight from New York to Tokyo. If you look at that flight path on a flat paper map, it looks like a bizarre, curving arc up near the Arctic, which seems completely irrational. Why wouldn't the plane just fly in a straight horizontal line across the map? The answer is that the map is flat, but the Earth is not. The plane is actually flying the shortest possible route across a curved surface, a great circle route, and that route only looks curved because you're viewing it on a flat projection. The plane isn't taking a detour. It's taking the truest possible straight line available on a sphere. Light bending around the sun works on exactly the same principle, just with one more dimension folded in. Light isn't detouring around the sun because some force reached out and yanked it off course. Light is traveling the geodesic, the truest, shortest, straightest path available, through a region of space-time that has been warped into a curve by the sun's mass. From light's own perspective, so to speak, it never turns at all. It's traveling perfectly straight the entire time. It's only from our outside vantage point, watching from a flatter region of space-time far from the sun, that the path appears to bend. This is the answer to the question in the title of this video, laid completely bare. Light bends around gravity, not because gravity reaches out and grabs. Mass, light has none to grab, but because gravity is the curvature of the very space and time that light, like everything else in the universe, has no choice but to travel through. There is no force involved at all in the Newtonian sense. There is only geometry. Light isn't being pulled off its path. There is no its path separate from the shape of spacetime. Light's path is the shape of spacetime traced out. I want to pause here because this deserves a moment of actual awe, not just information delivery. For your entire life, you have looked up at starlight and thought of it as arrows traveling in straight lines from distant points. occasionally getting deflected by objects in the way, like light bouncing off a mirror. What Einstein's equations actually describe is stranger and more beautiful than that. The light isn't deflected. The road it's walking on is bent. You are not looking at light that changed direction. You are looking at light faithfully, perfectly, obediently following a road that the sun itself carved into the fabric of reality between you and that distant star. Now, here's the part that connects this directly back to that factor of two mystery I promised you in the last section, because it's about to become the single most important twist in this entire story. The twist that turned Einstein from an obscure physicist into a global celebrity overnight. When Einstein first used only the equivalence principle back in 1911, treating gravity as pure acceleration, without yet accounting for the curvature of space itself, only the curvature of time, he calculated that starlight grazing the edge of the sun should bend by 0.87 arcseconds. That's an almost unimaginably tiny angle. For comparison, 1 arcsecond is the angle a coin would subtend from about 4 kilometers away. But by 1915, once Einstein completed the full mathematics of general relativity, properly accounting for the curvature of both space and time together, not just time, his prediction doubled to 1.75 arcseconds. Exactly double the earlier number. Why does that factor of 2 matter so much? Because it meant there were now 2 competing, precise, falsifiable predictions on the table. Newton's corpuscular theory of light, treating photons as tiny massive particles subject to ordinary gravity, predicted a bending of about 0.87 arcseconds, the same number Einstein got from his incomplete 1911 calculation. Einstein's completed 1915 theory of curved spacetime predicted exactly double that, 1.75 arcseconds. These were not vague, philosophical differences. They were 2 specific numbers that could be measured, if only someone could figure out how to actually see starlight bending near the blinding light of the sun. That single measurement, resolving whether the universe would say 0.87 or 1.75, would settle, in one photograph, whether gravity was Newton's invisible pulling hand or Einstein's curved geometry of spacetime itself. And in 1919, an expedition set out to 2 remote locations on Earth, chasing a total solar eclipse to take that photograph. We're going to go there next, but first, quick gut check. If you've followed everything up to this point, you now understand something that most people who've heard the phrase, gravity bends light, have never actually understood. Why it bends, not just that it bends, that's rare. That already puts you ahead of most casual explanations you'll find anywhere else. Drop a comment telling me the last time a video actually made a straight line feel like it could be curved, because that's genuinely what just happened in your head, whether you noticed it or not. Stick around, because in the next section, we go to a tiny volcanic island off the coast of West Africa in 1919, where a British astronomer risked his scientific reputation, his career, and arguably international scientific relations in the shadow of a war that had just ended, all to photograph a shadow. May 29, 1919, a tiny volcanic island called Principe off the west coast of Africa. A British astrophysicist named Arthur Eddington is standing beside a telescope, staring up at a sky that has just gone dark in the middle of the afternoon, waiting for clouds to clear during the few precious minutes of a total solar eclipse. Because this eclipse is the only moment on Earth when a very specific, very strange experiment becomes possible. Here's what will blow your mind about the stakes of this single afternoon. World War I had ended barely 6 months earlier. Einstein was a German physicist. Eddington was a British Quaker and pacifist. In an era of raw, bitter animosity between Britain and Germany, a British scientific expedition was setting out, at real financial and reputational risk, to try to prove that a German physicist's theory was correct, potentially overturning Isaac Newton, arguably Britain's own most celebrated scientific hero, in the process. Eddington believed deeply that science should transcend national rivalry. He was about to test that belief with a telescope pointed at a black disk in the sky. Let's understand exactly why an eclipse was necessary in the first place. Because this is a beautiful piece of practical problem solving. To measure how much starlight bends as it grazes past the sun, you need to see stars that appear, from Earth's point of view, to be located almost directly behind the sun, close enough to its edge that their light has to pass right by the sun's gravitational field on its way to your telescope. But under normal daylight conditions, this is obviously impossible. The sun is roughly 400,000 times brighter than starlight. You cannot see even the brightest star anywhere near the sun's position in the sky, because the sun's glare completely overwhelms everything else. During a total solar eclipse, though, the moon passes directly between the Earth and the sun, blocking the sun's blinding disk completely for a few minutes. And suddenly, stars that would normally be invisible, positioned near the sun's edge, become visible against a darkened sky. The plan was elegant in its simplicity. Photograph the star field around the sun during the total eclipse. Then, months later, photograph that exact same star field at night, when the sun is nowhere near it, so you have a baseline undisturbed position for each star. Compare the two photographs. If the stars near the sun's edge appear to have shifted position, even by a tiny fraction of a degree, compared to their true undisturbed positions, that shift is a direct measurement of how much the sun's gravity bent their light on its way to Earth. Eddington led one expedition to Principe. A second team, led by Andrew Crommelin, traveled to Sobral in Brazil as a backup in case weather ruined one location. This was smart redundancy, and it turned out to matter because clouds partially interfered with observations at Principe, forcing Eddington to work with only a handful of usable images. Here's mind-blown moment number 4, and it's a human one, not just a scientific one. Eddington developed the photographic plates himself, on location, working through the nights following the eclipse, using primitive equipment by any modern standard. Glass photographic plates, hand-measured under a microscope, comparing star positions to fractions of a millimeter. There was no computer to crunch the numbers. There was no instant digital comparison. Every single measurement was done by eye, by hand, with painstaking care, knowing that the entire result, proving or disproving one of the most audacious scientific claims in history, rested on measurements smaller than the width of a human hair. And the results came back squarely in Einstein's favor. Not Newton's 0.87 arcseconds, Einstein's 1.75 arcsecons, or close enough to it, given the observational uncertainty of the era, that scientists at the time considered it a decisive confirmation. On November 6, 1919, the results were announced jointly at a meeting of the Royal Society and the Royal Astronomical Society in London. J.J. Thomson, the physicist who had discovered the electron and was presiding over the meeting, called it one of the greatest achievements in the history of human thought. The next day, the front page of the Times of London read, "Revolution in Science, New Theory of the Universe, Newtonian Ideas Overthrown." Einstein, virtually unknown to the general public the week before, became a global celebrity within days. Now, think of it like this, because I want this moment to land the way it deserves to land. Imagine spending your entire life believing the world is flat, based on everyday experience that seems to confirm it perfectly. The ground looks flat, water looks flat, and nothing in your daily life ever contradicts it. Then one afternoon, someone shows you a single photograph, taken from just the right angle, at just the right moment, that proves the world was curved the entire time, and you simply never had the vantage point to see it. That's what happened to physics on November 6, 1919. Newton's gravity had worked well enough for 232 years, because in the low gravity conditions of everyday life on Earth, Newton's equations and Einstein's equations produced nearly identical predictions. It took a total solar eclipse and starlight bending around the most massive object in our solar system to reveal the difference. Here's a retention hook before we push further, because what I'm about to say completely reframes everything you've absorbed in the last 12 minutes. The 1919 eclipse wasn't the end of this story. It was barely the opening chapter. Eddington's measurement had an error margin large enough that some historians have since debated exactly how conclusive it really was in isolation. What actually cemented general relativity as correct wasn't one measurement. It was decades of increasingly precise tests using increasingly exotic tools that all kept confirming the same curved space-time prediction over and over in situations far more extreme than a total solar eclipse. And some of those situations are so bizarre, so far outside ordinary human experience, that they will make the bending of starlight around our sun look almost gentle by comparison. Because here's what's coming next. What happens when you don't just curve space-time a little, the way our sun does, but curve it so much that light doesn't just bend, it gets trapped entirely, circling forever or vanishing completely from the universe as we can observe it? What happens when the rubber sheet isn't gently dipped by a bowling ball, but punched clean through by something with the density of an entire star compressed into a single point? We're about to leave the relatively gentle bending of starlight around our sun and step into the realm of black holes, objects so extreme that Einstein himself, upon seeing the first exact mathematical solution describing them in 1916, wasn't even sure they could exist in reality. Stick with me. This is where things stop being merely surprising and start being almost impossible to fully accept, even once you understand the math perfectly. What if I told you that somewhere in the universe, right now, there are regions of space where light doesn't just bend, it orbits, circles, goes around and around a single point in a perfect loop, the same way the moon orbits the Earth, except the thing doing the orbiting is a beam of light itself, traveling at the fastest speed anything can travel in this universe, and it still cannot escape. This is one of the strangest, most genuinely mind-bending consequences of everything we've built so far, and it comes from a solution to Einstein's equations discovered astonishingly fast, within about a month of Einstein publishing General Relativity in November 1915. A German physicist named Karl Schwarzschild, while serving on the Russian front during World War I, found an exact mathematical solution describing the space-time curvature around a perfectly spherical, non-rotating mass. He mailed his solution to Einstein from the battlefield. He died a few months later from an autoimmune disease contracted during his military service, likely never fully realizing what his own equations implied. Schwarzschild's solution contained something startling. A specific radius, now called the Schwarzschild radius, at which the curvature of space-time around a sufficiently compact mass becomes so extreme that not even light can escape. Compress the mass of the Earth down into a sphere about the size of a marble, roughly 9 millimeters across, and you'd create a black hole. Compress the sun down to about 3 kilometers across, and the same thing happens. Nothing about the mass itself changes. What changes is the density, the compactness, and therefore the curvature of space-time immediately around it. Here's mind-blown moment number 5, and it directly answers the strange claim I opened this section with. Just outside the absolute point of no return of a black hole, a boundary called the event horizon, there exists a very thin, precise spherical shell of space called the photon sphere. At this exact distance, space-time is curved so severely that light traveling perfectly sideways, tangent to the black hole, doesn't fall in and doesn't escape either. It bends into a perfect circular orbit, chasing its own tail forever, trapped in a geodesic loop. It's an inherently unstable orbit. The slightest nudge sends the light either spiraling in or spiraling away. But for that one, theoretically perfect trajectory, light genuinely does orbit a black hole like a tiny moon made of pure electromagnetic radiation, traveling at 299,792 kilometers per second and still going nowhere. Let's ground this in something you've actually seen with your own eyes, because this stopped being pure theory in 2019. On April 10, 2019, the Event Horizon Telescope collaboration, a coordinated global network of 8 radio telescopes, spanning locations from Antarctica to Spain to Hawaii, effectively synchronized to work as one telescope the size of planet Earth, released the first ever direct image of a black hole, specifically the supermassive black hole at the center of the galaxy M87, roughly 55 million light-years away, with a mass about 6.5 billion times that of our Sun. What you see in that famous image, a glowing, lopsided orange ring surrounding a dark central shadow, is not the black hole itself. Black holes, by definition, emit no light. What you're actually looking at is superheated gas and plasma swirling around the black hole in an accretion disk, with its light bent by the extreme curvature of spacetime into that characteristic ring shape, including light from the far side of the black hole, bent up and over the top and around underneath, so that we see portions of the disk that should, by ordinary straight-line optics, be completely hidden behind the black hole itself. Think of it like this. Imagine standing behind an enormous, perfectly smooth glass sphere with someone standing directly on the other side, hidden from your direct view. Now imagine that sphere is so dense, it warps the space around it, and instead of the person being invisible to you, their image gets bent and smeared around the entire circumference of the sphere, so you can see a distorted version of them wrapping all the way around the edge, even though a straight line from your eyes to them is completely blocked. That's essentially what's happening in the Event Horizon Telescope image. You are seeing light from behind the black hole, bent around it and delivered to your eyes. The same fundamental principle as the 1919 eclipse starlight, just turned up to an intensity that breaks ordinary intuition entirely. Here's a second image that made history. On May 12, 2022, the same collaboration released an image of Sagittarius A*, the supermassive black hole at the very center of our own Milky Way galaxy, about 27,000 light-years from Earth, with a mass around 4 million times that of our Sun. That means, right now, as you're watching this, there is a black hole at the literal center of the galaxy you live in, and humanity has a photograph of its shadow, made entirely of gravitationally bent light. Now, let's connect this back to the core theme of this entire video, because I don't want this to feel like a detour into black holes for their own sake. This is the same phenomenon we started with, just dialed up to its most extreme possible expression. Starlight bending 1.75 arcseconds around our Sun during the 1919 eclipse, and light bending completely around a black hole into a perfect ring during the Event Horizon Telescope observations are not two different phenomena. They are the exact same physics, light following geodesics through curved spacetime, differing only in degree. The Sun curves spacetime gently, producing a small, precisely measurable deflection. A black hole curves spacetime so extremely that the gentle deflection becomes total capture, or a perfect circular orbit, or a full 180-degree redirection of light that would otherwise have been completely hidden from view. There is a term for the broader family of effects we've been discussing, and it's worth naming clearly here: gravitational lensing. Any sufficiently massive object, a star, a galaxy, a cluster of galaxies, a black hole, can act as a lens, bending the light of objects behind it, sometimes distorting their apparent shape, sometimes magnifying them, sometimes even producing multiple duplicate images of the exact same background object, because light from it took several different bent paths to reach us, arriving as if from several different directions at once. We will come back to this term, because it turns out to be one of the most powerful tools astronomers have ever had for studying the invisible structure of the entire universe, including something that has absolutely nothing to do with light itself, and everything to do with a substance we still cannot directly see or touch. But before we go there, I want you to sit with something for a moment, because this is where the emotional weight of this topic starts to build. Every photon of starlight that has ever reached your eye, from every star you've ever looked up and seen, traveled a path shaped by the mass of everything it passed near on its journey. asteroids, planets, stars, entire galaxies. In a very real, physically precise sense, the light hitting your retina right now has been sculpted by the gravitational fingerprint of the universe itself before it ever reached you. You are not looking at raw, untouched light. You are looking at light that has been shaped by everything it traveled past to get here, including, in the most extreme cases we know of, black holes that bent it into perfect circles before letting it continue on its way to you. We're at roughly the 1/3 mark of this journey. In the next section, we're going to push even further into the strange relationship between the bending of light and the slowing of time near massive objects, a connection that leads directly into one of the most beautiful confirmed predictions of general relativity. Gravitational waves, ripples in spacetime itself, first detected on Earth in September 2015, exactly 100 years after Einstein's theory was published. Stay with me, because that discovery involved two black holes doing something to spacetime that makes everything we've discussed so far look almost calm by comparison. Here's a question that sounds simple and isn't. If light bending near massive objects is really about spacetime being curved, and spacetime is space and time fused together, then shouldn't gravity be bending time too, not just the path light travels through space? What if I told you that a clock sitting on the floor of your house right now is ticking very, very slightly slower than a clock sitting on a shelf above it, and that this isn't a hypothetical? It's been measured on scales as small as a single foot of height difference. In 2010, physicists at the National Institute of Standards and Technology used optical atomic clocks so precise they could detect time dilation from an elevation change of just 33 centimeters, about 1 foot. The clock closer to Earth's center and slightly more curved spacetime ran measurably slower than the one raised higher up, exactly matching Einstein's predictions. This is called gravitational time dilation, and it's not a metaphor, and it's not a rounding error. It's a real physical effect that has been engineered around in real technology. The GPS correction I mentioned earlier being the most practical daily example. Now here's where this connects directly, powerfully, back to bending light. And this is going to be mind-blown moment number 6. So give this your full attention. Light doesn't just bend in curved space-time because the spatial path is warped. Part of the bending, and this was actually the part Einstein got wrong in his earlier 1911 calculation, the part that produced that half-strength 0.87 arcsecond number, comes specifically from the curvature of time near a massive object, not just the curvature of space. Regions of space-time closer to a massive object experience time passing more slowly. Light traveling through a region where time is running slower effectively behaves as though it's moving through a denser medium, similar to how light slows down and bends when it passes from air into water. An effect called refraction, which you've genuinely seen with your own eyes every time you've looked at a straw appearing to bend where it enters a glass of water. Think of it like this. Picture a marching band walking in a straight line across a field, all in perfect step, all moving at exactly the same speed. Now imagine one edge of that line steps onto a patch of thick, muddy ground, while the other edge stays on dry, firm grass. The muddy ground side of the line slows down, while the dry grass side keeps moving at full speed. Even though every single band member is trying to walk perfectly straight, the entire line will pivot and curve toward the muddy side, purely because of the difference in speed across the line, with no one intentionally turning at all. Light passing near a massive object experiences something conceptually similar. The side of the light wave passing closer to the mass moves through more severely time-dilated, more curved spacetime, and the side passing farther away moves through comparatively less warped spacetime, and this asymmetry bends the light's path. Even though light isn't a marching band and there's no mud involved at all, it's a geometric consequence of Einstein's equations. But the marching band captures the intuitive shape of why an unequal warping across a beam of light produces a bend. This is exactly why Einstein's original 1911 calculation, based only on the equivalence principle and gravitational time dilation, gave half the correct answer, 0.87 arcseconds instead of 1.75. He had correctly accounted for the curvature of time, but not yet the curvature of space itself. Once his full 1915 theory accounted for both effects together, curved time and curved space, working in tandem, the prediction doubled to match what Eddington's 1919 eclipse photographs actually showed. That factor of 2 isn't an accident or a coincidence. It's a direct, quantifiable signature that light bending near mass comes from two distinct geometric effects added together, and nature confirmed both halves were needed to get the right number. Now let's go somewhere almost unbelievably strange, because this same curved space-time framework predicts something Einstein himself doubted would ever actually be detected: gravitational waves. If mass curves space-time and that mass moves accelerates, changes its distribution, then the curvature of space-time itself should ripple outward, like dropping a stone into a pond, except the pond is the fabric of reality itself, and the ripples travel outward at the speed of light, stretching and compressing space as they pass through it. On September 14, 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, detected exactly this for the first time in human history. Two black holes, roughly 29 and 36 times the mass of our Sun, spiraled into each other and merged, roughly 1.3 billion light-years away, in a collision so violent that for a fraction of a second, it radiated more power and gravitational waves than the combined light output of every star in the observable universe put together. By the time that ripple in space-time reached Earth, 1.3 billion years later, it stretched and compressed LIGO's two 4-kilometer-long detector arms by an almost incomprehensibly small amount, roughly 1/10,000th the width of a proton. Physicists Rainer Weiss, Barry Barish, and Kip Thorne received the 2017 Nobel Prize in Physics for making this detection possible. Here's why this matters for our story about bending light. That black hole merger event didn't just ripple space-time. It also, in the process, provided one more spectacular confirmation that Einstein's geometric picture of gravity, the same picture that explains why light bends around the sun, holds true even in the most violent, extreme gravitational events imaginable, involving objects so dense that light itself is trapped inside them entirely. The bending of a beam of starlight by 1.75 arcseconds around our gentle, ordinary sun, and two black holes crashing together with enough energy to visibly ring space-time itself across more than 1 billion light-years. These sit on the exact same continuous scale of curved space-time physics. Same equations, same underlying geometry, just wildly different degrees of intensity. I want to bring this back down to something personal for a moment, because we're approaching the section of this video where we start connecting all of this cosmic scale physics to you, specifically sitting wherever you're sitting right now. Every single atom in your body and every photon of light reaching your eyes at this exact moment exists inside a universe where space and time are not the fixed, absolute stage that human intuition insists they are. They are flexible. They respond to the presence of mass and energy. They curve, stretch, ripple, and even trap light entirely, given enough density. And you have spent your entire life, every single day, standing inside a very slightly curved region of space-time, created by the mass of the Earth beneath your feet, bending time so gently that you'd never notice without an atomic clock, and bending the path of light so gently that it's imperceptible in daily life, but real, always right now, as you watch this. We're roughly 40% of the way through this journey. In the next section, we're going to take the concept of gravitational lensing, the same bending of light we've been building throughout, and use it to explain how astronomers have mapped something that has never directly emitted or reflected a single photon of light in the history of the universe: dark matter. And I promise you, Once you see how scientists manage to see something invisible using nothing but bent starlight, you will never look at a night sky photograph the same way again. Here's a genuinely strange question to sit with. How do you photograph something that has never, in the entire history of the universe, emitted, absorbed, reflected, or interacted with a single photon of light? What if I told you astronomers have done exactly this, not by seeing the invisible thing directly, which is by definition impossible, but by watching what it does to the light of everything behind it, using the exact same bending of light physics we've spent this whole video building? This is dark matter, and it might be the most quietly astonishing application of everything we've covered so far. Starting in the 1930s, astronomer Fritz Zwicky studied the motion of galaxies within the Coma galaxy cluster and noticed something wrong. The galaxies were moving far too fast to be held together by the gravity of only the visible matter he could observe. Something invisible had to be contributing extra gravitational pull, or the cluster should have flown apart long ago. In the 1970s, astronomer Vera Rubin, studying the rotation speeds of stars within individual spiral galaxies, found the same problem on a smaller scale. Stars at the outer edges of galaxies were orbiting far faster than the visible mass of the galaxy could explain, unless a huge amount of unseen matter, arranged in a roughly spherical halo, was contributing additional gravity. For decades, this remained somewhat abstract, inferred indirectly from orbital speeds, but never seen in any direct sense. And astronomers realized they had a tool sitting right in front of them, the exact tool this entire video has been building toward. If dark matter has mass, and mass curves spacetime, and curved spacetime bends the path of light passing through it, then dark matter, despite being completely invisible, should still act as a gravitational lens, bending and distorting the light of any background galaxies behind it, exactly the way our sun bent starlight in 1919, just on an unimaginably larger scale. Here's mind-blown moment number 7. When astronomers point telescopes at massive galaxy clusters, they frequently observe background galaxies that appear stretched, smeared, and warped into long, curved arcs, sometimes even duplicated into multiple distorted copies of the same galaxy, appearing in several places in the image at once. This is called strong gravitational lensing, and by carefully mapping the exact pattern and degree of this distortion, astronomers can mathematically reconstruct the full three-dimensional distribution of mass responsible for it, including all the invisible dark matter, even though not one single photon involved in that calculation ever touched, reflected off, or originated from the dark matter itself. They are mapping something they can never directly see, purely by measuring how it bends the light of things behind it. One of the most dramatic confirmations of this technique came from the Bullet Cluster, a system formed by the collision of two massive galaxy clusters, studied intensively starting in 2006, when astronomers combined X-ray observations, which show the location of hot visible gas, the vast majority of a galaxy cluster's ordinary visible matter, with gravitational lensing maps showing where the actual mass was concentrated. They found something remarkable. The visible gas was located in one place, having collided and slowed down during the cluster collision, while the gravitational lensing mass, the dark matter, had passed straight through the collision largely undisturbed, ending up somewhere else entirely. The mass and the visible matter were in two different places. This is considered one of the strongest pieces of direct observational evidence that dark matter is real, is not simply missing ordinary matter we failed to detect, and interacts with the universe overwhelmingly through gravity alone. Through exactly the same space-time curving, light-bending physics we've been describing this entire video. Think of it like this. Imagine a completely dark room with no light source of any kind, but with an enormous invisible boulder sitting somewhere in the middle of it. Now imagine you shine a flashlight from one side of the room and watch the shadow the light casts on the opposite wall. Even though you can never see the boulder directly, you can map out its exact size, shape, and position with tremendous precision. purely by studying the distortion pattern of light and shadow it creates. Dark matter mapping through gravitational lensing works on the same basic principle, scaled up to the size of galaxy clusters spanning millions of light years, using the light of background galaxies instead of a flashlight beam, and the distortion in their shapes instead of a shadow. Here's where this becomes genuinely staggering in scope. Based on decades of these lensing studies, combined with other independent lines of evidence, current estimates suggest that dark matter makes up roughly 27% of the total mass energy content of the universe, compared to only about 5% for all the ordinary matter that makes up stars, planets, gas, dust, you and me combined. The remaining 68% or so is an even stranger, still poorly understood phenomenon called dark energy, responsible for the accelerating expansion of the universe. Discovered in 1998 through observations of distant exploding stars called Type Ia supernova, work that earned Saul Perlmutter, Brian Schmidt, and Adam Rees the 2011 Nobel Prize in Physics. Sit with that ratio for a moment, because it deserves real weight. Everything you have ever seen with your own eyes, every star, every planet, every galaxy visible through the most powerful telescopes ever built, every photon of starlight we discussed bending around the sun in 1919 comes from roughly 5% of what actually exists in the universe. The other 95% we know exists almost entirely because of how it bends light in warp spacetime. Using precisely the physics, this entire video has been carefully building, one layer at a time, since the very first minute. This is where I want to start shifting how we're talking about all of this, because up to this point, we've mostly been building understanding, layer by layer, concept by concept, from Newton's force-based gravity, through Einstein's equivalence principle, through curved spacetime, through the 1919 eclipse, through black holes and gravitational waves, and now through the invisible architecture of dark matter itself. Starting in the next section, I want to turn this lens, pun very much intended, back onto you, and onto what it actually means to exist as a conscious being inside a universe built this way. Because here's the thing worth sitting with as we cross into that next chapter. You are made of roughly 5% of the universe's contents, standing on a planet held in orbit by curved spacetime, illuminated by light that bends slightly on its way to warm your skin, existing inside a cosmic structure 95% of which is fundamentally invisible to you, detectable only through its gravitational fingerprints on the small sliver of reality you actually can perceive. If that doesn't reframe how you think about your own place in all of this, wait for what's coming next, because we're about to talk about what all of this means, not for astronomers with telescopes 1,000 light years away, but for you, personally, right now, in the chair you're sitting in. I want to ask you something, and I want you to actually sit with it rather than skip past it. When was the last time you thought about the fact that you are, physically, a curved space-time phenomenon? Not metaphorically, literally. Your body has mass. Your mass curves the space-time immediately around you by an amount so vanishingly small it will never register on any instrument humanity has ever built. But the curvature is not zero. It is real. Every person you've ever loved, every person who has ever lived, has spent their entire life gently warping the fabric of reality around their own body, all day, every day, without a single one of them ever noticing. Here's what I want to explore with you now, because we've spent 7 sections building the physics, and it's time to ask what it actually means to live inside a universe that works this way. Think about the picture we've built. Newton gave humanity a universe of forces, invisible hands reaching across empty space, pulling on things, a universe where objects were fundamentally separate from each other, connected only by tugging influences passing between them. It's a lonely picture, in a way. If you think about it long enough, the sun over there, the earth over here, bound together by an invisible rope of force stretched across 93 million miles of nothing. Einstein gave humanity something different, And I think it's worth pausing to notice how different it actually is, emotionally, not just mathematically. In Einstein's universe, there is no rope. There is no invisible hand reaching across the emptiness. There is no over there and over here, separated by a gap that force has to bridge. Instead, everything, every star, every planet, every photon of light, every atom in your body exists as part of one single, continuous, unified geometric structure. The sun doesn't reach across space to pull the Earth. The sun and the Earth are both simply features embedded within the same curved fabric, each one shaping the very geometry the other one moves through. Gravity isn't a message sent between separate things. Gravity is what it looks like when things are not actually separate in the first place, when they are all threads in the same weave. What if I told you that this reframes something most people carry around their entire lives without ever examining, the sense that we are small, isolated points of consciousness, adrift in a vast, cold, indifferent emptiness, disconnected from everything around us except by faint, tenuous forces? Einstein's universe doesn't actually support that picture, not really. In a universe made of curved spacetime, rather than forces acting across a void, there is no true emptiness in the way we imagine it. Space itself is an active, responsive, participatory medium. It bends in response to your mass. It carries the imprint of every object that has ever existed within it. And light itself, the very thing that lets you see and be seen, is constantly, continuously, being shaped by that shared structure as it moves between you and everything else in the universe. Here's a way to think about it that I find genuinely moving, and this is mind-blown moment number 8, though it's less about a specific fact and more about a shift in perspective. Every time you look at a photograph of a distant galaxy cluster, bending the light of something behind it, or a black hole's shadow rendered in bent light, or even just a solar eclipse, you are not looking at light and gravity interacting as two separate systems bumping into each other. You are watching a single unified structure, space-time, displaying itself. The bending isn't a collision, it's a signature. It's space-time writing its own shape, using light as the ink, and you, watching, are reading a message written directly into the geometry of existence, using nothing but your own eyes and a beam of ancient light. Let's bring this even closer to home, because I don't want this to stay abstract. Right now, as this light from your screen reaches your eyes, it is traveling through space-time that is curved, ever so slightly, by the Earth beneath you, by your own body, by the device in your hands, by every object in the room around you. You have never, not once in your entire life, experienced a truly flat, uncurved region of reality. Every photograph you've ever taken, every sunset you've ever watched, every face you've ever looked into and recognized, all of it has been light bending, subtly, imperceptibly, but really, through the curved shape carved into space-time by your own presence and the presence of everything and everyone around you. Here's a way to think about it that connects to something almost everyone has felt at some point, usually late at night: the strange, quiet sense of insignificance that can creep in when you really think about the scale of the universe, all those billions of galaxies, all that unimaginable emptiness. Think of it like this. It's easy to look at the vastness of space and feel like a single grain of sand on an infinite beach, unnoticed, unremarkable, disconnected from all that immensity. But the physics we've spent this video building tells a quieter, stranger, and honestly, more beautiful story. You are not separate from that immensity. You are woven into the same fabric as the black hole at the center of our galaxy, as the light bent by our sun in 1919, as the dark matter holding entire galaxy clusters together across millions of light years. Not poetically, structurally. The same equations that describe the curve of space-time around a supermassive black hole 27,000 light years away describe, with the exact same mathematics, just at a vastly different scale, the infinitesimally small curve of space-time around your own body right now as you sit here. I want to give you something to actually do with this, not just something to feel, because understanding should change how you move through the world, even in small ways. The next time you're outside and you look up and see stars, or even just sunlight breaking through clouds, I want you to remember that what you're seeing has, in a very real sense, been touched by every massive object it passed near on its way to you, including, eventually, converging on the mass of your own body, however infinitesimally, as it arrives at your eye. You are not a passive observer of a universe happening somewhere out there, separate from you. You are an active participant in the geometry of reality, curving the space around you constantly, whether you've ever thought about it before this moment or not. We still have a lot of ground to cover. Some of the strangest, most reality-bending consequences of everything we've built are still ahead of us, including a question that even Einstein struggled with, about whether the universe treats the past, present, and future as fundamentally different at all, or whether that distinction might itself be something closer to a very convincing illusion. But before we go there, I want you to notice how you're feeling right now, sitting with everything we've covered. That mixture of wonder and slight vertigo, that's not a bug. That's the exact right response to genuinely understanding, even a little, how strange and interconnected the actual structure of reality is beneath the comfortable, flat-seeming surface of everyday life. Let's keep going. Here's a question that sounds almost childish, and isn't. Is now the same thing for everyone, everywhere in the universe, all at once? Almost everyone assumes yes, without ever examining it. What if I told you that general relativity, the same theory explaining why light bends around the sun, implies the answer is no, and that now, as a universal, shared, simultaneous moment stretching across the cosmos, might not actually exist at all in the way you've always assumed it does? This connects directly back to gravitational time dilation, which we touched on earlier, clocks running slower near massive objects, confirmed by atomic clocks sensitive to elevation changes of just 1 foot. But the implications run deeper than clocks tick at different speeds. Einstein's theory, both special and general relativity together, dismantles the idea of a single universal now entirely. Two observers moving at different speeds or sitting in regions of different gravitational curvature can genuinely disagree about which of two events happened first, and both can be correct according to their own reference frame, with no way to declare one of them objectively right and the other wrong. This isn't a limitation of measurement. It's baked into the actual structure of spacetime itself. Think of it like this, because I want this to feel tangible rather than purely abstract. Imagine two people reading the same book, but one of them is reading it in English, translated left to right, and the other is reading a version translated into a language written right to left. If they compare notes on what happens first in a given scene, they might describe events in a different order relative to their own reading direction, even though they're both reading the exact same underlying story, faithfully and correctly. Simultaneity in Einstein's universe is something like that, a matter of your particular reference frame, not an absolute fact stamped onto the universe from outside. Here's mind-blown moment number 9, and it circles all the way back to the light-bending physics we started with. Because light's path bends near massive objects, and because time itself curves near massive objects, the very concept of watching something happen gets stranger the closer you look. If you could watch a clock falling toward a black hole's event horizon from a safe distance, you would never actually see it cross the horizon, not because it doesn't happen, but because the light carrying the image of that clock takes longer and longer to climb back out of the increasingly severe space-time curvature as the clock approaches the horizon, appearing to slow down and redden, essentially freezing, fading, and becoming undetectably dim, asymptotically approaching, but never quite reaching the horizon from your outside perspective, even though, from the falling clock's own perspective, it crosses the horizon in a perfectly ordinary, finite amount of time, without any local drama at all. This is genuinely one of the strangest confirmed consequences of general relativity. Two completely different, equally valid descriptions of the same event, depending entirely on where you're standing and how space-time is curved between you and what you're observing. There isn't a real version that one observer sees correctly and the other sees incorrectly. Both are true in their own reference frame simultaneously, because the light connecting them has to travel through curved space-time to get from one to the other. And that curvature genuinely changes what happening and now even mean across that gap. Now here's how I want to bring this back to something personal, something worth actually feeling rather than just understanding intellectually. Every single now you've ever experienced, every moment you've called the present, has only ever reached you filtered through light that traveled through curved space-time to arrive at your eyes. When you look at the sun, you're not seeing the sun as it is now. You're seeing light that left it roughly 8 minutes ago, bent very slightly along the way by the sun's own mass and by the Earth's mass as it arrived. When you look at the nearest star beyond our solar system, you're seeing light over 4 years old. When you looked at that Event Horizon Telescope image of the black hole at the center of galaxy M87, you were looking at light that left that black hole's surroundings 55 million years ago, before humans existed on this planet in any form. Bent into that glowing ring shape by space-time curvature so extreme, it trapped some of that light forever, letting only a portion escape to eventually, after a 55 million year journey, reach a network of radio telescopes on Earth in April 2019. You have never once in your entire life seen the universe as it is right now. You have only ever seen the universe as it was, filtered and bent through curved space-time on its long journey to your eyes. Every photograph, every glance at the night sky, every moment of watching sunlight fall across a room is an act of looking directly into the past, a past that has been quietly, continuously reshaped in transit by the gravity of everything it passed near, including, in the final infinitesimal fraction of that journey, your own body's mass, curving the last few feet of space between the light and your retina. Here's what I think is genuinely worth sitting with emotionally as part of this entire journey. There's something almost tender about this, if you let yourself feel it rather than just process it as information. Every connection you have ever had to the universe beyond your own body, every sunset, every star, every photograph of every cosmic phenomenon we've discussed in this video has traveled to you through a universe that bends, warps, and curves in response to mass and energy, carrying with it the gravitational fingerprint of everything along its journey, before finally, gently, bending one last time around the mass of your own body, delivering an ancient message into your eye in this single moment you're calling now. We are now past the 1 hour mark of understanding some genuinely advanced concepts most people never encounter outside of a university physics course, and you're still here. That says something about you, a real, genuine curiosity about how the universe actually works beneath the surface, rather than settling for the comfortable, simplified version most people carry around unquestioned. If that describes you, if you felt that pull throughout this video, drop a comment with one word: curious. I want to see how many of you have made it this far, because what's coming in the next several sections is going to take everything we've built about bending light, curved space-time, and the illusion of a universal now, and push it toward the single strangest, most actively debated open question at the frontier of modern physics. What happens to information, to light, to the very structure of reality itself, at the absolute center of a black hole, where our current understanding of physics simply stops working? Let's go there next. What if I told you that inside every black hole in the universe, hidden behind the event horizon we discussed earlier, sits a place where the equations of general relativity, the exact same equations that correctly predicted the 1.75 arcsecond bending of starlight in 1919, the exact same equations confirmed by gravitational waves in 2015, the exact same equations behind every image the Event Horizon Telescope has ever captured, completely break down and stop producing meaningful answers at all? This is the singularity, and it might be the single strangest, most honestly uncomfortable concept in all of modern physics, precisely because it represents the edge of human understanding itself, not just a strange but fully explained phenomenon. Here's the setup. Carl Schwarzschild's solution, the one he mailed to Einstein from the battlefield in 1916, doesn't just describe the event horizon we discussed earlier. It also describes what should exist at the very center of a black hole, mathematically. A point where all the mass that fell in has been compressed into a region of, according to the raw math, zero volume and therefore infinite density, infinite curvature of spacetime, infinite tidal forces. The equations that beautifully, precisely describe the gentle bending of starlight around our sun, when pushed to this extreme, simply stop returning sensible numbers. They return infinity, and in physics, when your equations return infinity for a physically real quantity, that's usually not nature telling you something is actually infinite. It's usually physics telling you that your theory has reached the edge of where it applies, and something new is needed to describe what's really happening. Think of it like this. Imagine you have a beautifully accurate map of a coastline, so precise it can guide a ship safely through complex channels and around rocky outcrops with total confidence. That map is genuinely, reliably useful, right up until the coastline suddenly narrows into a region the mapmakers never actually surveyed. Maybe a cave system running deep underground, completely unmapped. Your map doesn't necessarily draw the cave system incorrectly. It just stops having any data there at all. And if you try to extend the map's existing style and rules into that blank region anyway, you'll likely draw something wrong, because the tool that worked beautifully for the coastline was never designed to describe what's happening underground. Singularities are physics's blank spot on the map, a place where general relativity, magnificently successful everywhere we've been able to test it, from bending starlight to detecting gravitational waves, admits it doesn't have the right tools to describe what's actually happening. Here's mind-blown moment number 10. Physicists overwhelmingly believe that the true resolution to this problem will come from a theory of quantum gravity, a still unfinished framework that successfully merges Einstein's general relativity, which beautifully describes gravity and the large-scale structure of the universe, including all the light-bending phenomena we've covered, with quantum mechanics, which beautifully describes the behavior of particles and forces at the smallest scales, but which, as of today, in 2026, has never been successfully unified with gravity into one complete, experimentally confirmed theory. String theory, loop quantum gravity, and several other competing frameworks all attempt to solve this puzzle in different ways, predicting that the true center of a black hole isn't an actual infinite density point at all, but something else entirely, a tiny, unimaginably dense but finite structure that our current mathematics simply isn't equipped to describe yet. This remains one of the most actively pursued open questions in theoretical physics today, and whoever eventually resolves it convincingly with testable predictions will very likely receive science's highest honors. I want to be honest with you about something, because I think intellectual honesty matters more than manufactured certainty, especially on a channel built around real science. We do not currently know what is actually happening at the center of a black hole. Anyone who tells you with total confidence exactly what's down there is going beyond what the evidence and the math currently support. What we do know, with tremendous confidence, backed by over a century of increasingly precise experimental confirmation, from the 1919 eclipse to atomic clock experiments to GPS satellite corrections, to gravitational wave detections, to actual photographs of black hole shadows, is everything leading right up to the edge of that singularity, the event horizon, the photon sphere, the extreme curvature of spacetime, the bending of light into perfect circular orbits. All of that is remarkably well tested and confirmed. It's only the very, very center, the singularity itself, where our current physics runs out of road. Here's why I find this genuinely beautiful rather than frustrating, and I want to try to convey why. Science's greatest triumphs have almost always come from precisely these moments, the edges where our best theories admit their own limits. Newton's gravity worked magnificently for over 2 centuries, until light bending near the sun revealed its limits. And that limit is what led directly to Einstein's deeper, more complete picture. General relativity has now worked magnificently for over a century, confirmed again and again in increasingly extreme conditions. But the singularity at the heart of every black hole is relativity's own honest admission of where its usefulness runs out. Exactly the same way Newton's theory eventually admitted its limits near the sun in 1919. That's not a flaw in science. That's how science is supposed to work, a beautiful mechanism for finding exactly where our understanding needs to grow next. Let's take this personally for a moment, because I think there's something worth extracting from this that goes beyond black holes entirely. Every one of us, at some point, reaches the edge of our own understanding about something. A relationship we can't quite make sense of. A decision we can't fully calculate the consequences of. A piece of our own life where the equations we've relied on for everything else simply stop producing clear answers. The instinct, in those moments, is often either to panic or to pretend we understand more than we actually do, papering over the uncertainty with false confidence. Physics, at its very best, models a different response. Acknowledge the edge honestly, keep gathering better tools, keep refining the map, and treat the blank spot not as a failure, but as the exact location of the next real discovery waiting to happen. The scientists working on quantum gravity right now aren't embarrassed that they don't have the answer. They're energized by exactly the fact that this genuine, honest gap in human knowledge still exists actively in 2026, waiting for someone curious enough to close it. We've now covered the extremes, the total bending of light into circular photon orbits, the trapping of light entirely behind an event horizon, and the honest edge of human knowledge at the singularity itself. In the next section, I want to pull back out from these extremes and show you something almost unbearably vast. How gravitational lensing, the very same bending of light phenomenon that started this whole video with a single 1919 eclipse photograph, has become one of the most powerful tools astronomers have for looking back toward the very beginning of the observable universe itself, magnifying and revealing galaxies so distant and so faint that without gravitational lensing, acting as nature's own free telescope, we would have no way of ever detecting them at all. What if I told you that some of the most distant galaxies humanity has ever detected, galaxies whose light has been traveling toward us for over 13 billion years, from a time when the universe itself was still in its infancy, were only discovered because of light bending, the exact phenomenon we started this entire video with? This is gravitational lensing, used not as a curiosity, but as a genuine scientific instrument, nature's own telescope built entirely out of curved spacetime, with zero cost to construct and a magnifying power that no human-built telescope could ever match on its own. Here's how it works, tying directly back to everything we've built. When a massive foreground galaxy cluster sits directly between Earth and a much more distant background galaxy, its gravity curves the spacetime around it, bending the background galaxy's light along multiple paths on its way to Earth, exactly as we described with the Booley cluster and dark matter mapping earlier. But there's a bonus effect beyond just distortion. This bending can also magnify and brighten the background galaxy's light, sometimes by factors of 10, 20, or even more, acting as an enormous, naturally occurring magnifying glass spanning millions of light years across. Astronomers using the James Webb Space Telescope, launched in December 2021 and delivering its first full images in July 2022, have deliberately pointed the telescope at massive foreground galaxy clusters, specifically to take advantage of this gravitational magnification, using it to detect background galaxies so distant and so intrinsically faint that even Webb's extraordinary infrared sensitivity would likely not have been able to detect them without the extra boost from gravitational lensing. Some of these observations have revealed galaxy candidates that appear to date back to within a few 100 million years of the Big Bang itself. Light that has been traveling toward Earth for over 13 billion years. Arriving now, having been bent, magnified, and delivered to us by the gravity of everything it happened to pass by along that unimaginably long journey. Think of it like this. Imagine trying to read a very small, very faint sign on the far side of a lake at night, from a great distance, with nothing but your naked eye. Now imagine that, purely by geometric accident, a curved, polished surface happens to sit between you and that sign, focusing and magnifying the faint light coming from it, making it suddenly, dramatically readable in a way it never would have been otherwise. Gravitational lensing does exactly this at a cosmic scale, using the curved spacetime of entire galaxy clusters as the polished surface, turning some of the faintest, most ancient light in the observable universe into something modern telescopes can actually detect and study. Here's mind-blown moment number 11, and I think it might be the most quietly staggering fact in this entire video. Every one of those ultra-distant galaxy images, bent and magnified by gravitational lensing, is showing us the universe as it looked when it was a small fraction of its current age. The universe was born roughly 13.8 billion years ago, based on current cosmological measurements, and some of this lensed light left its source galaxies when the universe was under 500 million years old, meaning we are looking at light that has been traveling, bending, and being bent again by everything it passed near for over 96% of the entire history of the universe, before finally arriving at a mirror on a telescope orbiting a small planet around an ordinary star that didn't even exist yet when that light began its journey. This connects back, in the most profound way I can offer in this video, to the very first minutes of what we discussed. A 1919 eclipse measured starlight bending by 1.75 arcseconds around our sun. A tiny, precise, local demonstration of curved spacetime, using light that had traveled a mere 8 light minutes before reaching the sun's edge on its way to Earth. What we're describing now is the exact same underlying physics, the exact same geodesic following, force-free, geometry-only bending of massless light, operating across a canvas so large it encompasses essentially the entire visible history of the universe. From 8 light minutes to 13 billion light years, same principle, same equations, same fundamental truth about what gravity actually is, just scaled up by a factor of roughly 800 trillion. I want to slow down here and let this land, because I think it's easy to hear a number like 13 billion light years and let it wash over you as just another big, abstract figure, the way we often do with astronomical scales. But think about what it actually means for you, specifically right now. The light from some of these ultra-distant lensed galaxies began its journey before Earth existed, before our sun existed, before the Milky Way galaxy had even fully formed into the shape we recognize today. That light traveled, uninterrupted, bending gently around countless galaxies and clusters along its way for well over 13 billion years, arriving at a moment in cosmic history. Right now, this year, this exact minute, when a species capable of understanding gravity, capable of building space telescopes, capable of reconstructing the entire bent path that light traveled to reach us, happened to exist on a small rocky planet to receive it, look at it, and understand, at least partially, what it's actually showing us. There's something in that timing worth sitting with honestly. Out of the roughly 13.8 billion year history of the universe, humans have possessed the scientific understanding to explain why that light bends the way it does for only about a century, since 1915. Out of the entire vast expanse of cosmic time that ancient starlight traveled through, it arrived at almost precisely the narrow, recent sliver of time when creatures existed who could actually make sense of it. You happened to be alive during that sliver. Not humanity in some abstract, distant sense. You, specifically right now, watching this video, exists during the tiny fraction of cosmic history when this understanding has finally become possible. We're now well past the halfway point of this deep dive, and I want to acknowledge something before we continue into the next stretch, because the concepts ahead get genuinely more abstract, touching on the philosophical edges of what physics can even claim to know. If you've made it this far, through Newton's force-based gravity, through Einstein's equivalence principle, through the 1919 eclipse, through black holes, gravitational waves, dark matter, the illusion of a universal now, the honest limits of our knowledge at singularities, and now the deepest gravitational lenses ever used to peer toward the beginning of time itself, you have built, piece by piece, a genuinely sophisticated, accurate mental model of one of the most important ideas in modern physics. That's not a small thing. Most people go their entire lives without ever building this. Take a breath. In the next section, we're going to ask what all of this actually implies about the nature of reality itself, and what it might mean that the universe seems to be built at its deepest level, not out of solid, separate objects pushed and pulled by forces, but out of pure relational geometry. Here's a question I want you to actually try to answer for yourself, honestly, before I offer any kind of response. If gravity isn't a force, if it's simply the shape of space-time, and if mass and energy are what determine that shape, does that mean the universe is, in some deep sense, made of geometry itself, rather than made of things the way we intuitively imagine? This is the kind of question that sits right at the boundary between physics and philosophy. And I want to be careful and honest as we walk through it, because this is exactly the territory where people sometimes take real, established science and stretch it into claims it doesn't actually support. So let's be precise about what the physics actually says, and where the more speculative interpretive layer begins. What general relativity establishes, with an enormous body of confirmed experimental evidence behind it: the 1919 eclipse, atomic clock experiments, GPS corrections, gravitational wave detections, black hole imaging, is that space-time is not a passive, fixed backdrop against which events happen. It is dynamic. It responds to mass and energy. It curves, and that curvature is what we experience as gravity, including the bending of massless light that started this entire video. This is not philosophical speculation. This is measured, confirmed, repeatedly tested physical fact. What becomes more interpretive is the leap towards statements like, the universe is fundamentally made of geometry, or objects are just patterns in space-time. These are genuinely popular and defensible ways some physicists and philosophers of science talk about the implications of general relativity, but they represent an interpretation of the mathematics, not a directly measured fact in the same way the light-bending angle itself is. I want to hold that distinction honestly, because part of respecting real science is not blurring the line between what we've confirmed and what some of us find compelling to conclude from it. With that honesty established, here's what I think is fair to say, and it's still genuinely mind-bending, mind-blown moment number 12. The deeper you go into general relativity, the harder it becomes to draw a clean line between the stage and the actors, between space and time as a container, and the objects and events that happen within it. Mass tells space-time how to curve. Curved space-time tells mass how to move. This is almost word for word how the physicist John Wheeler, who also coined the term black hole in 1967, famously summarized general relativity. Notice what that sentence actually implies. It's not a one-way relationship, container holding contents. It's a continuous feedback loop, an ongoing conversation between geometry and matter, each one constantly reshaping the other. In that sense, empty space, as most people imagine it, a passive inert nothingness that things simply sit inside, may not be the most accurate way to think about the universe at all. Space-time, in Einstein's picture, is less like a stage and more like a living, responsive material. And everything that exists, including you, is simultaneously being shaped by it and actively shaping it in return. every single moment. Think of it like this. Imagine a vast piece of fabric stretched out, and imagine that every single thread within that fabric is somehow also a tiny weaver, constantly adjusting the tension and weave of the threads immediately around it, while simultaneously being shaped by the tension of every other thread nearby. There's no clean separation between the fabric and the weavers. They are the same system, at the same time, mutually defining each other continuously. That's closer to how modern physics actually describes the relationship between mass, energy, and spacetime than the simpler image of solid objects sitting inside an empty, unchanging void. Now let's connect this back to the emotional and personal thread we picked up a few sections ago, because I think this geometric picture of reality has something genuinely useful to offer beyond pure information. If the universe is not fundamentally made of separate, isolated objects connected only by forces reaching across empty gaps, if it is, instead, a single continuous structure in which everything is mutually shaping everything else, all the time, at every scale, from a photon bending around your body's mass to a black hole warping light across 55 million light years, then the entire framework of thinking about yourself as a small, isolated thing cut off from everything around you by empty distance may be capturing something less true about reality than it feels like it's capturing. You are not a separate object placed into an empty universe. You are a genuine, active participant in one continuous, responsive geometric structure, constantly and mutually shaping and being shaped by everything around you, whether or not the effect is large enough for any instrument to register it. I want to be careful here, because I don't want to overstate this into some kind of vague mysticism that the actual physics doesn't support. That would betray the intellectual honesty this whole video is tried to maintain. General relativity does not say that your thoughts, or your consciousness, or your intentions curve spacetime in any special way beyond the ordinary gravitational effect of your body's mass, which is real, but genuinely, thoroughly negligible on any meaningful scale. What it does say, rigorously and confirmed by over a century of increasingly precise experiments, is that the universe's actual architecture, the thing underneath the comfortable, everyday illusion of solid objects separated by empty space, is a single, continuous, dynamically interconnected geometric structure. And every single massive thing within it, including you, is a genuine structural part of that architecture, not a visitor passing through an indifferent void. Here's where I want to leave this section, because it's a genuine bridge into what's coming. If gravity taught Newton's era that the universe runs on forces, invisible influences reaching across a fundamentally empty stage, then gravity, properly understood through Einstein's eyes, teaches something quieter and, I'd argue, more beautiful, that the universe runs on relationship, on the mutual shaping of everything by everything else. That separateness itself, the deep intuitive sense most of us carry that we are isolated points of experience surrounded by empty distance, may be less a fact about the actual structure of reality and more a limitation of the scale at which human perception operates. In the next section, we're going to take this idea somewhere I think you'll find genuinely surprising, into the strange, actively debated relationship between gravity, information, and one of the most contested unsolved puzzles in modern theoretical physics. What actually happens to information that falls into a black hole, and why some of the smartest physicists alive today, including Stephen Hawking himself before his death in 2018, spent decades fundamentally disagreeing about the answer. Stay with me. This next part connects the bending of light all the way to the very definition of what it means for something to exist and to be remembered at all. Here's one of the strangest, most genuinely unresolved puzzles in modern physics, and it comes directly from combining everything we've built about bending light, curved spacetime, and black holes with one of the deepest principles in all of physics. Information can never truly be destroyed. What if I told you that this simple, almost sacred rule of physics appears to come into direct, head-on conflict with what black holes seem to do, and that resolving this conflict occupied some of the greatest physicists of the last 50 years, including a very public, decades-long disagreement that ended with one of them conceding a bet in front of an audience. Let's build the setup properly. In quantum mechanics, there's a deep principle called unitarity, which essentially guarantees that information about the state of a physical system is always in principle preserved and recoverable, even if it becomes scrambled beyond any practical hope of reconstruction. Burn a book, and the information about its exact contents doesn't vanish from the universe. It just becomes smeared out into smoke, heat, and ash in a way so complex that no realistic process could ever reassemble it. But the information is still, in principle, encoded somewhere in the universe's total state. In 1974, Stephen Hawking made a discovery that would trouble him and the entire field of theoretical physics for decades. Combining general relativity with quantum mechanics, he predicted that black holes are not, in fact, perfectly and eternally stable, as Schwarzschild's original 1916 solution suggested. Instead, they slowly emit a faint form of radiation, now called Hawking radiation, through a subtle quantum effect happening right at the edge of the event horizon. And over unimaginably long timescales, this radiation causes black holes to lose mass and eventually fully evaporate. Here's the problem, and it's mind-blown moment number 13. Hawking's calculations suggested that this radiation is purely thermal, essentially random, structureless, carrying no actual information about whatever fell into the black hole to create or feed it in the first place. If that's true, then when a black hole fully evaporates, all the information about everything that ever fell into it, including light, bent along its geodesic path into the event horizon, exactly the phenomenon we've spent this video exploring, genuinely, permanently vanishes from the universe, with absolutely no possibility of ever being recovered, even in principle. This directly violates unitarity, one of the deepest, most fundamental, best-tested principles in all of quantum physics. This became known as the black hole information paradox, and it represents a genuine, still not fully settled collision between general relativity and quantum mechanics. The same two theories physicists are still struggling to unify. The same struggle underlying the unresolved mystery of what actually happens at a singularity, which we discussed a few sections ago. In 1997, physicist Kip Thorne, the same Kip Thorne who later shared the 2017 Nobel Prize for the LIGO gravitational wave detection, made a public bet with Stephen Hawking, wagering that information really is lost inside black holes, while physicist John Preskill bet the opposite, that information must ultimately be preserved in keeping with quantum mechanics. In 2004, Hawking publicly conceded the bet to Preskill, having become convinced, through further theoretical work involving the mathematics of string theory, that information likely is preserved after all, though the precise physical mechanism by which this happens remains an active, unresolved area of cutting-edge theoretical research even today. In 2026, involving concepts like the holographic principle, which suggests almost unbelievably that all the information about everything that falls into a black hole might actually be encoded on the black hole's two-dimensional event horizon surface itself, rather than genuinely lost inside the three-dimensional volume behind it. Think of it like this, to try to grasp why this matters so much to physicists. Imagine a library where every book that has ever been written is, according to the fundamental rules governing that library, never allowed to be truly destroyed. Even if a book gets thrown into an incinerator, physicists insist that, in principle, if you could track every single photon of heat and every wisp of smoke produced by the fire with perfect precision, you could theoretically reconstruct exactly what the book originally said, because that information didn't vanish, it just scattered. Now imagine discovering an incinerator so powerful, so fundamentally strange, that it seemed to violate this rule entirely, genuinely, permanently destroying the information inside anything thrown into it, with no scattering, no scrambling, no theoretical path back to reconstruction at all. That apparent incinerator is what a black hole looked like under Hawking's original 1974 calculations. And an enormous amount of theoretical effort over the following 50 years has gone into showing that black holes are not actually that kind of incinerator after all. That somehow, through mechanisms still being actively worked out, the information does survive, encoded in a form we don't yet fully understand how to read. I want to connect this back, directly and deliberately, to the very core theme of this entire video, because I think it closes a loop in a genuinely satisfying way. This whole story began with a simple, seemingly impossible fact. Light, despite having zero mass, bends around massive objects because gravity isn't a force acting on mass. It's the geometry that everything, including massless light, has no choice but to travel through. We've now followed that single idea from a 1919 eclipse photograph, through black holes, gravitational waves, dark matter, the illusion of a universal now, the honest limits of physics at a singularity, and all the way to one of the deepest open questions about whether information itself, the very thing that makes anything knowable, rememberable, or real in a meaningful sense, can survive its encounter with the most extreme gravitational curvature the universe produces. Here's what I want you to sit with as we head toward the final section of this journey. Every photon of light that bends around the sun, around a black hole, around a distant galaxy cluster on its way to your eyes, is, in a very real sense, carrying information about where it came from, about everything it passed near on its journey, about the shape of space-time itself along its entire path. When you look up at the night sky, you are not just receiving light. You are receiving information, faithfully carried across unimaginable distances and unimaginable time, bent and shaped by gravity the entire way, arriving intact enough for you to look up, understand at least part of what you're seeing, and in this exact moment, know something true about the structure of reality that took our species over 200 years, from Newton to Einstein to Hawking to the Event Horizon Telescope collaboration, to figure out. We have one section left, and I want to bring everything we've built, every scientist, every experiment, every mind-bending revelation, back to a single, final grounding idea about what it means to be a conscious, curious being, capable of understanding even a fraction of this, alive on a small planet, orbiting an ordinary star, bending the light around you in a way no other species on Earth has ever been able to comprehend or explain. Let's finish this together. We started this journey with a single, seemingly impossible fact. Light has no mass, and yet it bends around massive objects. And for over 200 years, the best scientific framework humanity had simply couldn't explain why. Now, after everything we've built together, I want to walk back through exactly what you actually understand, because I think it's important to see how far you've genuinely come, not just abstractly, but specifically, piece by piece. You now understand that Newton's gravity, brilliant and useful as it was for over 2 centuries, described gravity as a force acting between masses, and that this framework, taken at face value, predicts light should be completely unaffected by gravity, because light has no mass for that force to act on. You understand that Einstein, starting from a simple thought experiment about a person in a windowless elevator, realized that gravity and acceleration are physically indistinguishable, his happiest thought, and that this single insight, followed rigorously through the mathematics, led to the conclusion that gravity isn't a force at all, but the curvature of space-time itself, a single 4-dimensional fabric weaving space and time together into one continuous structure. You understand that light, despite having zero mass, still has to travel through that curved fabric, following the straightest possible path available to it, a geodesic, and that this path appears bent to an outside observer, not because light was pulled off course, but because the very geometry it was traveling through was never straight to begin with. You understand that this wasn't just philosophy. It was a testable, falsifiable prediction, and that Arthur Eddington, in 1919, traveled to a remote island off the coast of Africa during a total solar eclipse to photograph exactly this effect, measuring starlight bending by 1.75 arcseconds around our sun, precisely matching Einstein's completed theory and precisely doubling Newton's prediction. A single photograph that overturned 232 years of scientific consensus almost overnight. You understand that this same light-bending physics, taken to its most extreme conclusion, describes the photon sphere around a black hole where light can genuinely orbit in a circle forever, and that humanity has actually photographed this phenomenon directly, first at the black hole at the center of galaxy M87 in 2019, and then at Sagittarius A*, the black hole at the very center of our own Milky Way galaxy, in 2022. You understand that this same curved spacetime framework predicted gravitational waves, ripples in the fabric of reality itself, first detected by LIGO in September 2015, exactly 1 century after Einstein's theory was published, generated by two black holes spiraling into each other over 1 billion light years away. You understand that gravitational lensing, this same bending of light, has become one of astronomy's most powerful tools, used to map the invisible architecture of dark matter through objects like the Bullet Cluster, and used by the James Webb Space Telescope to magnify and detect some of the most distant, ancient galaxies ever observed, their light having traveled toward us for over 13 billion years. You understand that this framework reveals the illusion of a single universal now, that it honestly admits its own limits at the singularity hidden inside every black hole, and that it sits at the heart of one of the most actively debated open puzzles in modern physics, whether information itself can survive being swallowed by the most extreme gravitational curvature the universe produces. That is an enormous amount of genuine, accurate understanding. Most people who have heard the phrase, light bends around gravity, have never actually understood why in any real depth. You now do. Sit with that for a second. That's not nothing. That's the kind of understanding that changes how you actually see the universe, not just what facts you can recite about it. Now, I want to close with the part of this that I think matters most, the part that goes beyond the physics itself. Here's the question I want to leave you with. What does it mean that a species born on a small, unremarkable rocky planet, orbiting an ordinary yellow star, in an ordinary spiral arm of an ordinary galaxy, among literally hundreds of billions of others, managed to figure this out? Not just observe that light bends, figure out why, with such precision that we can now photograph the shadow of a black hole 55 million light years away, and have it match a prediction made on paper using nothing but careful thought and mathematics over a century earlier. Think of it like this, as a final analogy, and I want this one to actually stay with you. Imagine an ant, born on a single leaf of a single tree, in an enormous forest. It will never fully see or comprehend the size of, somehow working out, through nothing but careful observation and reasoning, the exact mathematical shape of the entire forest's canopy, the precise physics governing how sunlight filters down through every layer of leaves above it, and the exact structure of the roots spreading invisibly beneath the ground. It will never directly see. That is, genuinely, proportionally, something close to what our species has done with gravity, space-time, and the bending of light. We are extraordinarily small, extraordinarily young, as cosmic timescales go, and yet we have managed to reach out with nothing but curiosity, mathematics, and stubborn persistence, and correctly describe the behavior of light bending around objects millions of light years away, objects so extreme that light itself gets trapped inside them forever. I don't think that's a small thing to be part of. I think it's genuinely one of the most remarkable things about being human, that a species capable of fear, of pettiness, of getting distracted by trivial daily concerns, is also simultaneously capable of pointing a network of telescopes spanning the entire planet at a black hole, 55 million light years away, and correctly predicting, in advance, exactly what shape its shadow would take, because we understood the geometry of the space it was sitting in. You watching this video, understanding the concepts we've walked through together, are part of that same lineage of curiosity. The same lineage that includes Newton, working out his laws in the 1660s and 70s. Mitchell and Laplace, glimpsing the mathematical shadow of black holes over a century before Einstein. Einstein himself, working alone in a Swiss patent office. Schwarzschild, solving equations from a battlefield in the final months of his life. Eddington, risking his reputation to prove a rival nation's scientist correct in the aftermath of a devastating war. Hawking, wrestling for decades with the fate of information itself. And thousands of scientists and engineers, working together across continents to capture the actual photograph shadow of a black hole for the very first time in 2019. You are part of this lineage now too, simply by understanding it. That's not a small or symbolic thing. Understanding genuinely, accurately, why light bends around gravity changes how you look at the sun, at the night sky, at every photograph of every distant galaxy you'll ever encounter again. You will never look at a simple, ordinary solar eclipse the same way again, knowing that a photograph like that once overturned 2 centuries of scientific certainty in a single afternoon. Before you go, I want to ask you the same 2 things I asked back at the very beginning of this video, because I want to see how this specific community of curious minds has grown across the nearly 4 hours we've just spent together. Tell me where in the world you're watching this from, and what time it is right there for you as this video ends. And tell me, honestly, which single moment in this entire video hit you the hardest? Was it the elevator thought experiment, the 1919 eclipse, the photon sphere orbiting a black hole forever, the dark matter mapped through bent light we can never directly see, or the idea that every now you've ever experienced was actually light from the past, bending its way toward you across a universe that never stopped shaping it? If this video genuinely expanded how you see the universe, subscribe, because we go this deep every single week into ideas most channels never had the patience or the space to properly explain. There is so much more of the universe left to understand together, and I would be genuinely glad to have you along for it. Thank you for spending nearly 4 hours of your one finite, precious life inside this specific corner of physics with me. Given everything we've just walked through, about how deeply everything in this universe is connected, about how the light reaching your eyes right now has been shaped by every massive thing it ever passed, I don't think that's a small thing to have shared. I'll see you in the next one.